All right, so beginning in chapter 5, or lesson 5 as they call it, we want to just to kind of make sure we understand the term set when we're talking about sets of numbers. We learned the term natural numbers, and natural numbers are just the numbers that we count with. And so if we were to write that as a set, sets, you always use these curly braces, and I would say 1, 2, 3, 4, 5, dot, dot, dot. It just keeps going. Those would be our natural numbers, and that's how you would write those represented as a set. Now, how would this change if we were to say whole numbers? Does anybody know the difference? If we use the term whole numbers? It would be almost the same with one slight modification.
It involves negatives.
Huh?
It involves negative numbers too.
I can't hear you.
Negatives.
No, you're close. That would be the next one. So if we said integers, then we're going to include the negatives. All right? So if this one is dot, 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 we'll do like -3, -2, -1, 0, 1, 2, 3, dot, dot, dot.
All numbers start with 0.
They start with 0. Yes, who said that? Will?
Me.
Yep, so whole numbers start with 0. So we've got 0 and then all the other stuff that we had before. So it's a small distinction, but they will occasionally ask you some questions that have to do with whole versus natural versus integer. So make sure that you understand that definition. But the main thing we were trying to just teach you here is that we call this a set, right? When we have the curly braces on the outside and the numbers separated by commas, that's a set of numbers. In this case, this is the set of natural numbers. In this case, it's the set of whole numbers. And in this case, it's the set of integers.
When would you use whole numbers?
Well, maybe here's something that's just kind of real world, because this was my world for so many years. I'm still teaching it. In programming, we use whole numbers. So in programming, we don't typically start counting from 1. We start counting from 0. And so there are just, I can't think of another application off the top of my head, but that's definitely a world that whole numbers are important in. We have to always remember to start with 0 instead of 1. And I guess when you're just teaching kids concepts about numbers, right? You're not going to start with talking about negative numbers, because that's not it's kind of hard to represent that, right? But I could say, if I'm counting, right, the number of pens that I have, right now on the table I have 0 pens, right? Now I have 1, okay, technically it's a marker, 1. Now I have 2, right? So as we count, we just naturally, 0 is what we have to start with. Kids have to understand that. So just in the way that we think about stuff, you have to have this idea of 0, because that's when you don't have any, right? And then you move on. All right, so let's go on to talk about absolute value, and I'm hoping that a lot of this stuff is review, but we definitely always, when you're reviewing, there are concepts that you just didn't get well the first time that you learned it. So that's part of what we're trying to do in here, is making sure that we remember those concepts, that we understood those concepts the first time around. So when I talk about the absolute value of something, what does that actually mean?
They're both positive.
They're both positive, all right? So for the absolute value of positive 3 would be 3. The absolute value of negative 3 would also be 3. And so absolute value is just sort of the, if it's a negative number, you just drop the negative sign and say that it's the number without the negative sign. If it's the positive number, you don't have to do anything. It'll always be the same number. All right, what's the absolute value of 0?
Just 0.
It's just 0. All right, so if you're wondering is that some kind of special case? It's not. The absolute value is 0. So it's just always the number without any sign that's on the front of it is what we call the absolute value. If you, of course, have something where you've got something like this, how are you going to solve that?
You just get 9.
Yeah, you just subtract the 11. 11 minus 2, you do that subtraction first to get 9, and then the absolute value is 9. And if you had something that, what if you had this same thing here, but we had a negative sign in front of that? How would that change our answer, or would it change our answer?
It wouldn't.
Huh?
It
It
wouldn't.
wouldn't.
It wouldn't?
It always stay the same.
It would. The reason it would is because the negative is outside the absolute value. Okay, so because the negative is out here, we got to keep the negative out there. And then when we take the absolute value of 9, we still have that negative sitting out front. Okay, so the absolute value only applies to stuff that's inside the bars. That's sort of an important thing for us to grasp. The stuff outside the bars is unaffected by the absolute value. Okay, does that make sense to everybody? Now, again, I'm assuming this is probably review for most of you, but I want to make sure that you understand this. And number lines are often how we sort of think about this. I'm going to draw a number line here. 1, 2, 3, 4, 5, negative 1, 2, 3, 4, 5. So this is negative 5, this is positive 5. 1, 2, 3, 4. 2, 3, 4. And so if we had something like 3, if we just think about 3 minus 2, we all know that 3 minus 2 is 1, right? Super simple. We've been doing that type of arithmetic for a while. But I want to make sure that you grasp the fact that you can always think of any problem that's got addition and subtraction in it. You can really think of the whole thing as a sum. You can think of all of it as addition. And the way that you would do that is you would say, okay, well, this is a positive 3 here, right? Just to include the sign on there so we're clear on what it is, plus a negative 2. And that again is going to give us the same answer, 1. And so that kind of helps us when we sort of think about it on a number line. If we first go positive 3, so we're going to go all the way to here, right? And then from that positive 3, we want to add to that a negative 2. So we go back in the negative direction, 2. And so this will actually be our answer, which is a positive 1. So you can always think of numbers as sums, whether you're doing subtraction or addition. Just kind of think of it with the parentheses around it and then pluses in between there. And so that helps us when we're thinking about something like 2 minus 4. Same kind of thing, right? We've got a positive 2 plus a negative 4. And so it should make sense to us when we do that we've got the positive 2 there. We're going to add to that 4 in the negative direction. So we go back this way and we end up at negative 2. So that's going to give us a negative 2 for both of those. Of course, if we start with the negative numbers, we have something like negative 3 plus 1. That's negative 3 plus a positive 1. So on our number line, we go backwards this way, 3. And then we go in the positive direction, 1. So we get an answer of negative 2 for this one. And then finally, what if we have 2 negative numbers? Negative 2 minus negative 3. That's the same as negative 2 plus a negative 3.
It'd be negative 5.
It's going to be negative 5, right? So we start off here and we go negative 2 to get us to right there. And then we add to that another negative 3, which is going to get us all the way over here.
Like a multiplication with 2 negatives doesn't make a positive.
It does, yeah. So that's something we're going to talk about today as well. I'll tell you guys, when I see something like this, just kind of the quick way that I think about it in my brain, is anytime you see one number minus the other, you're always taking a difference. And so I always think of whatever the bigger number is minus the other one, because that's simpler for us to think about when it comes to subtraction, right? So the way that I think about it, like 2 minus 4, I think about that as 4 minus 2, because that's really easy for me to think about. What is 4 minus 2? That's just 2, right? And then I take whatever number is the bigger number here, whatever the sign is on the biggest number is going to be the sign on my answer. So since I've got a minus on the 4, then I have to put a minus in front of the 2. So you can always think of subtraction as a difference between the 2 numbers that are there, and then whatever the bigger number of the 2 is, you just apply that sign to it. So that's another way to sort of think about that in your head. I know for something like 2 minus 4, maybe that seems, well, that's not, why do I need to do that? Well, when you're dealing with bigger numbers, it becomes more of an issue, right? If I want to do like 25 minus 38, that maybe is a little harder for me to think about than 2 minus 4. And so the way I'm thinking about this is I'm thinking 38 minus 25. 38 minus 25 is something we can do in our head. What would the answer to that be? I mean, I can even do the subtraction in my head. I've got the numbers lined up in my mind. 35 minus 28. I'm sorry, 38 minus 25. Yes?
13.
It's just 13, right? So this is going to equal 13 when I take the difference of the two. And which number is bigger, the 38 or the 25? The 38 is. And so I'm going to take the sign from the 38 and put that in front. That's my answer. It's negative 13. All right? Does that make sense? Just kind of a trick in ways to sort of think about it. It might help your brain, like it helps mine, to think about it in that fashion. And I have to remember Juliana's daughter's name. Are you Alexa? Okay. See, what's going to happen now is whenever I meet my first cousin next time, I'm going to call her Alexa. You're going to totally have messed me up. Thanks a lot. All right, any questions about any of this stuff? It should be reviewed, but it's always good to just sort of refresh our minds concerning things like this. Make sure we've got, you'll learn little tricks that just make it a little easier next time. I want to make sure everybody knows this. With addition, we have the commutative property of addition. Does anybody know what that means, that addition is commutative? It means that it doesn't matter what order I add the numbers in, right? I can reverse the numbers when I'm adding together and add them in any order and I'll still get the same answer, right? We can do that on our number line and we can see whether I went 4 first and then 3, or if I went 3 first and then 4, we're still going to get the same answer. So addition is commutative, and we can always reverse the numbers around if it's easier for us to think about it like that, okay? And so that means when we have problems like this, 3 minus 2, since we can really even think of subtraction as addition, it also means that we can, if we've got several numbers like 2 minus 4 plus 3 minus 1, we can do those in any order, right? So yeah, instead of doing 2 minus 4 plus 3 minus 1, I could think of that as, 3 plus 2 minus 4 minus 1. I can think about it like that, and I would get the same answer. Let's just verify that's the case. If I do these in order, 2 minus 4 is?
Negative 2.
Negative 2 plus 3 is?
1.
1 minus 1?
Is 0.
Is 0, right? So I get 0 there. Let's see what I get when I do this one. 3 plus 2 is?
5.
Minus 4?
1.
1 minus 1?
0.
0. So I get the same answer either way. So sometimes it'll be easier to kind of reverse the order around. That's totally okay to do that when you've got a bunch of addition and subtraction, all right? Because of the commutative property of addition. So I think that gets us through that first section there. And really, I just kind of did the second section, so I think you guys will get that. Let me make sure that you are okay with the way that they write this, and so I'll write this example on the board. Negative 5 plus 4 plus negative 3 plus positive 2. So they've rewritten a problem that really would be negative 5 plus 4 minus 3 plus 2. And they've rewritten it like that to show that it's all just a bunch of addition, right? So you can kind of have the number line idea in your head and think through it like that. So what would this answer be here? Negative 4 plus a positive 4. Sorry, I should have had a plus here. Negative 5 plus a positive 4.
It's negative 1.
It's negative 1. Negative 1 plus a negative 3.
Negative 4.
Negative 4. And then a negative 4 plus a positive 2. Negative 2. All right? So just making sure that you can think about it that way. And it might help you when you have sort of a long, complicated problem with a bunch of addition and subtraction in it. Just think of it as a bunch of addition with positive and negative signs. Really, we want to get to the point where we don't have to write the parentheses in there, though we want to be able to do something like this, and it still makes sense in our heads. So let's just verify that. Let's walk through one more. All right. Negative 4 minus 3 is the same as negative 4 plus a negative 3. So that's what?
Negative 7.
Negative 7 plus 2. Negative 5 minus 4.
Negative 9.
Negative 9 minus 3. We're adding another negative 3, huh?
Negative 12.
Negative 12 minus 2.
Negative 14.
Negative 14. All right, so you got to be able to do that in your head. Yes.
Can I go to the bathroom?
Yes, you may. While I try to remember this student's first name is Allison. Why can't I remember that? All right, thank you. So we're through 6. Let's go ahead and go to number 7. What time do we get done in here?
11:10.
11:10. Sure, I keep an eye on the time. I'll probably ask you that every day, every week for the rest of the year, and you're like, surely he knows by now it's 11:10. But I just get so, I get engaged in the lesson, and I forget simple things like that. The school I was teaching at the other day, I let my students out like almost 30 minutes early because I got confused all the time. So you guys wouldn't let that happen, right? They just left and nobody said, why are you letting us out so early? They're like, oh, we get 30 extra minutes. All right. So anyway, the opposite of a number. We should know this concept, but if we have a 0 here, 1, 2, negative 1, negative 2. The opposite of 2 is what? It's not a trick question. What would we think of as the opposite of 2? Negative 2, right? So it's the number that's on the other side of 0, the same distance from 0, but in the other direction, right? So when we talk about the opposite of number, just think about reversing the sign. So since just like the opposite of positive 2 is negative 2, if I asked you for the opposite of negative 2, that would be positive 2, going in the other direction, right? So that's not a strange concept. But they want to make sure that you can do things like this. If I were to say, what is that? When you think of this idea of opposite, I'm going to start with negative 2 right here. So start with the inner parentheses.
Positive to negative.
Yeah, right? So we start with the number of the parentheses, so I'm right here. This negative in front here means take the opposite of that, so now I'm jumping over here, but then we've got a negative out front that says take the opposite of that, so now we're back to here, right? So this answer here would actually be negative 2. But then if I have something like this, I'm starting with negative 2, but then this sign here says take the opposite of that, so I'm jumping over here, and so this answer would be positive 2. Now you can think about it with number lines if that helps you to think about it that way. I don't think number lines at all with that sort of stuff. How do you guys think about it? Do you envision a number line in your head, or do you think something else when you see a bunch of negatives like this together? Will, you said something earlier that's more in line with the way that I think about it. Somebody have a different way to think about that? So the way that I think about it is the way you mentioned multiplication, right? You said that a negative times a negative, right? If I have negative 1 times negative 1, that's going to give me positive 1, right? A negative times a negative is a positive. And so I can think about all these negatives as just ones, right? Because if I multiply times a negative times a 1, that doesn't change the value of anything. And so the way that I think about it is, what if I have this? What if I have negative 1 times negative 1 times negative 1? What's that going to give me? Negative 1, right? Because a negative times a negative gives me a positive 1, but then a positive 1 times a negative 1 gives me a negative 1 again. So what I see, the pattern here is that if I have an even number of negative signs, I'll end up with a positive. And if I have an odd number of negative signs, so if we do 5 here instead of 4, that's going to give me a negative number. What do I have here? I have an odd number of negative signs, and so I'm going to end up with a negative sign. Yes?
Negative to the ratio.
Yes?
You said it's going to think of it differently. I think of it pretty different.
Okay.
I don't think of a line at all. I
Right.
think of bringing 2 down, and then the next 2 down, and the
Right.
next 2 down.
Yeah.
That way it's more, I feel like it's more set up for me to go, I don't have to go back and forth, back and forth.
And so is it kind of like this? So you bring these, do you start here or do you start over here?
I'd start usually from the beginning to end, but since this one you work your way in, out,
Right.
I just bring it down. from
Yeah,
the
so you
inside.
see these two negatives and you go, that's a positive.
Yep.
Right? And that positive times this negative, bring those down, that
Yes.
becomes negative. Yeah. So that's kind of the way that I think about it as well. But when you've got a bunch of them together like this, you can simply look at it and say, I've got 3, which is an odd number, so it's going to be negative. I've got 2, which is an even number, so it's going to be negative. If I were to add some more negatives in the front here, so maybe I were to do this, and then maybe I'll put these out front here and put another negative in there. 1, 2, 3, 4. We've got 4, that's an even number of negative signs. I could think about it like she said, bring these 2 down, that's a positive. Positive times a negative, bring those 2 down, that's a negative. Negative times a negative is a positive. Or just recognize there are 4 negatives, and that's going to give me a positive number at the end. Okay? So there's multiple ways to think about it, and you're going to get an opportunity to practice a lot of that, right? But just don't get confused. Don't get confused and lose your place when you're counting up these negative signs. Like they have a problem in here that looks like this. And this is actually a homework problem. So it's, but in that program homework problem, you've got. Let's just work through this one because it's a little bit longer. All right, so where am I gonna start a problem like this? Which where?
The very first parentheses.
Parentheses, right? So the order of operations says pay attention to your parentheses first, specifically your inner parentheses. So when you said parentheses, are you wanting me to start here or right here? This one, right? So we'll start with the inside one first. So we're going to take this in steps. Once you get good at this, you don't necessarily have to do all these steps, but I just want to make sure that everybody's connecting the dots. All right, so we're going to start there. And so we're going to say, we're going to keep this here, we're going to keep this one here, like this, and we're just going to deal with what this parentheses has here. So we've got a -4, and we're taking the negative of a -4, so that's going to give us a what? A +4. So now we can take all of this and just reduce it down to +4, right? We've still got something, brackets inside of something else, so let's continue to work on that. So we've got, I'll leave our curly braces there. We've got the negative of a +4, so what's this going to give me? A -4, right? Now we can start thinking, okay, we don't have any parentheses or brackets inside other things. So now we can start just kind of getting rid of all of our parentheses. What is this minus a -3 become? What's the right way to think about that? So what am I changing this to?
A positive.
I'm going to do +3, right? Now, if you want to, you can think about it like this. This is the same as -2 plus minus a -3. I just wrote bigger and smaller parentheses. You can think about it like that. The negatives and the negatives together are going to give me a positive. Right? So I can just rewrite that as -2 plus 3. If you need to take that step for right now, take that step for right now. But I'm just looking at it and going, I've got 2 negative signs. 2 negative signs together become a positive sign. So I'm going to write it like that. And then I've got the same thing here, 2 negative signs together. So I'm going to write it like that. Once I get it like that and I get rid of all my parentheses, then I'm just going to do the addition and subtraction in order, right? So -2 plus 3 is what? 1, and 1 plus 4 is 5. So that would be our final answer for that one. Okay? So again, I don't think this is anything groundbreaking or earth-shattering that you haven't seen before, but some of you may not be good at this, right? It may just be something that you haven't done a lot of, and it's easy for you to get confused. Maybe you just see all those minus signs and your brain goes, I don't know, right? But just take it in pieces, just like we did here. You could have kind of done a shortcut for this one. If you'd followed our rule a minute ago with all of our, when I was talking about all of the number of signs that you have in place will determine what your final sign is. And so I'm looking at this thing and going, this right here, I've got a minus, 1, 2, 3, 4 negative signs. So I know at the end of the day, this whole thing's just going to be a positive, right? And this thing here, I've got a minus and a minus. So 2 of those, I know this is going to be a positive, and this is going to remain a -2. So -2 plus 3 is +1 plus 4 is 5. So that's sort of a shortcut route to get it if you want to go that way. Okay? All right. So last of all, let's talk about area. You guys done area problems before? Right? You probably saw that in pre-algebra. What is area? If I think about a shape like this here.
It's the distance all around. That's perimeter.
That's perimeter, yeah.
The distance in the inside.
In the inside. So we're talking about how much space is this thing taking up, right? And so the way that we think about that is like if I were to draw this as 2 and 4 like this, we think about that as having
it's kind of like a graph with finding area.
think about it as 1 by 1 squares all inside there, right? And so each of these are 1 by 1. And if you count up all the 1 by 1 squares inside there, 1, 2, 3, 4, 5, 6, 7, 8, then we would say that the area of this entire figure would be 8 units squared. If this is 4 inches and this is 2 inches, then we would say it's 8 inches squared. Now we're not gonna, yes?
So basically you just multiply the two numbers?
Exactly, that's what I was gonna say. We're not actually gonna write squares and count those up, right? For all of these different shapes, we've got a formula that we can remember. But that's where the formula comes from. It's this idea of thinking, if we had a bunch of 1 by 1 squares in there, what would the area be? And so for this one, go ahead.
If it was like a shape, like a, let's say a stair set, what would you do? Like, would you multiply more than 2 numbers?
So you're saying like this here?
Or like just something that's not like the same length.
Yeah, right. So, okay, we'll talk about that. If it gets too complicated, if you've got something like this, you're gonna have to learn calculus to do it.
Okay.
All right, but at the end of the day, you're still thinking the same thing. You're trying to do a bunch of little squares and you use calculus to estimate what these curvy areas would be, right? Because at some point you're going to hit a curve and you're like, that's not a whole square. How am I supposed to do that? So calculus, that's a big part of what you're learning in calculus, is determining the area of odd shapes like this, all right? That is certainly beyond the scope of this class. And I had to take 5 calculuses in college, and I forgot most of that, so I don't know that I can even tell you how to do it. When you talk about, one of them is, the calculus terms are, you have integrals and you have derivatives. And I think it's the integral that you use to find weird areas like that, but don't quote me on that, I could be wrong. So our basic rule for, what do we call this basic shape here? Huh?
Rectangle.
A rectangle. And so for a rectangle, the easiest thing to do is just to memorize the area. So the area of a rectangle is, if we define this as the length and we define this as the width, it's just the length times the width, right? So as Allison noted, we could just multiply 4 and 2 together. Did you say that, Allison? You didn't? Who said that? Oh, Alexa did. All right, so just multiply the 4 and the 2 together, right? The length is 4 inches, the width is 2 inches, and so we say 4 times 2 is 8. For the inches, an inch times an inch is inches squared. And so that would be our final answer, if we're talking about a rectangle. And so they just give you the area of a rectangle, it's length times width. The area of a square, you can think of in a very similar way. If you defined it as length times width, it would have the exact same area. I mean, it would have the exact same formula as a rectangle, but what's unique about a square compared to a rectangle? Yes?
That has equal sides all around.
All the sides are the same length. So for a square, we can just say the length of this side is S, and so that's obviously the length of this side as well. And so the area of a square is S times S, and S times S is just S squared. So we can just think about the length of the side squared is the area for a square. Now what if we have something more complicated that doesn't require calculus, like Will asked about? What if we have a set of stairs like this, right? And we're told that the height, let me do it where it's a little, they're weird stairs, so they're like longer, like this, all right? So we're trying to find the area underneath these stairs, and we know that the height of each of these guys is 1, but then we can think of it as the width, whatever. And this is the length, so this is 2 for each of these guys.
You split them up.
What's that?
You split them up.
So you just split them up, yeah. So we think, well, right here I've got a little rectangle, right? Right here I actually have what? Huh? I have 2 rectangles,
You have a square.
but I technically have a square. A square is technically a rectangle, by the way. It's just a special rectangle where both the sides have the same length. Do you see that? The length of this side is 2. So the top is 2 and the bottom is 2. The length of this side is 1 here. And then here I've got another rectangle, right, which has a length of 3, or a width of 3, depending on how you're looking at it, and a length of 2. And so we've got 3 different figures, and so we can just take the area of each one. The area of the first, we'll just label that the area of the first one, is going to be what?
2.
What 2? It's just 2, because I'm multiplying together 1 and 2. So my final answer there, we'll say all of these are in feet. So our final answer there is going to be feet squared. Area is always going to have a unit of whatever your units are squared. So that's the area of box 1. We'll label this box 1 just to be super confusing. This one box 2, and this one box 3. And so the area of box 2 is what?
4.
4, right? Because it's just 2, this length here and this length here. So 2 times 2, or that length squared. Actually, the way that we gave you the area of a square was it's the length of the side squared. So 2 squared is 4 feet squared. And then finally, the area of rectangle 3 is going to be 2 times 3, which gives us 6 feet squared. So for the total area of the squares, we'll just say A subscript T to represent area total is going to be 2 plus 4 plus 6 feet squared. And so that's going to be 12 feet squared would be our total area underneath the stairs. Okay? Let me ask you guys to do something too while I'm thinking about it. Do me a favor and always circle or put a box around your answer whenever you're doing putting your answers on here. Because I'm just saying, when I look at something like this, and you're not the only one, Ada, when I look at something like this, it's like, man, there's writing all over the place. Which one goes with which problem and which one's the answer. So if you'll circle it for me, and Ada actually did. As I'm looking at this, I can see that she's got areas circled. So that's a huge help to me if you will just circle or box it off so I'll know which one is actually your answer. Okay? Any questions about how you do this? All right. So what if you had something, so they give us an example in the book where you had, let's say you have a figure like this that, we'll just make one up, it's a little bit different. So this is a square here, the length of 4 and 4, but then inside here, you have a rectangle. We're going to shade that in because it's like a hole in our square. And this is going to be 1 and 2 for that. And they ask us, what's the area of the non-shaded portion of our figure? How would I figure that out?
You just multiply 2 and 1. For the non-shaded?
Yeah, the non-shaded area. So I'm trying to get all of this area out here.
You multiply 4 times 4 and then take away 2 from where the box is.
Yeah, so I'm going to take the area of the square outside here, which is 4 times 4, or 4 squared, right? And then I'm going to subtract from that the area of my little rectangle inside here, which is going to be 2 times 1. So that's going to be 16, we'll say this is in inches, So that's going to be 16 here minus 2, and it's going to give me a final value of 14 inches. What? Since it's in the area, so it's going to be inches squared, right? That would be my final answer. Any questions about that? So they're going to give you a bunch more formulas, a lot more formulas for area, and I'm just going to kind of write those on the board to make sure we have all of those in a nice, concise fashion. So we're going to do them in this order. What did I say the area of a square was? If I make the length of the side S, what's the area of my square?
They're all the same size.
So it's going to be is S squared, right? If I have a rectangle, then I'll label length times width, and the area of my rectangle is going to be, I said length times width already. That's the area of my rectangle, length times width. What if I have a circle with a radius of, that we'll just write as R? Does anybody know what the area is, Madeline? Pi r squared, right? The area of a circle is pi r squared. So for example, if our radius is 2, then my area, we'll say the radius is 2 there. We'll say 2 centimeters. And so the area of my circle is pi times 2 squared, which is going to be pi times 4. And for these types of problems, you're always welcome to leave pi in the answer, unless I tell you explicitly not to, which means I can just write this as 4 pi. You always put your number in the front when you do that. Yep. Were you asking about that? Yeah, so you always put your number in the front because you think of pi as a variable. And so anytime we're writing, we wouldn't say A3 if that's or let's say you have an equation like this, x squared 2 plus x3 minus 1. We would never write it like that. We would say 2x squared plus 3x minus 1. Because these numbers on the front here, they're what we call coefficients for those variables. And so you always put the number in the front. And in this case here, pi is sort of acting like a variable for us. It's a variable that represents 3.14, da 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 da. In here, in this class, you can always use pi, just round it to 3.14. Pi is one of those numbers that's an irrational number. And do you guys know what that means? Yeah?
It basically never ends.
Yeah, it never ends. There's no repeating that goes on. So it just keeps going and going and going. So we'll just use 3.14 in here. If you wanted to get a decimal version of this, you would do 4 times 3.14 to get the decimal version. Am I done? Since I said you could leave pi in your answer, am I done with that? What else do I have to do? I've already squared it. So I've got an answer with pi in it, and this answer is correct, but we're missing one thing that you always need to put on problems like this. Anybody see it?
Centimeters?
Who said that? Centimeters, is it just centimeters?
Squared.
Centimeters squared, right? Area is always units squared. So don't forget your units. I remember the name, I just don't remember if you spelled it with a Y? Okay, so is it like, is it 2 N's?
L-I-L-Y.
Oh, L-I? Lily, yeah, not Lee, I'm sorry. I was saying Liliana in my head, but L-I-L-Y-A-N-A, like that? Okay, cool. So don't forget your units. Your units are super, super important, and you need to get in the habit of putting those in there. You'll hear, if you take my chemistry class, a brief story about the, I think it was the Mars expedition, where they were 2 different sets of one person that used metric units and another person that used English units that were working on the same project. And so it was like this kind of Mars rover thing that they were sending, and it crash landed on the planet because they didn't write their units down, and one assumed that the unit that the value that was down there was 1 unit, and it wasn't. So always put your units so that we know what you're talking about. In addition to the area of a circle, you need to also know how to find the area of a triangle. And so I'm just going to write 3 different types of triangles, because these are the 3 that you will encounter. This one here is a right triangle, Here we have an acute triangle, and then we're going to have an obtuse triangle here. All right, and so for each of these guys, it's important that we understand that this is our base. So B is here, B is here, and B is here. So whatever that length is there would be our base. And for the right triangle, this represents our height. But for this acute triangle here, we have to think of a dotted line that goes all the way down and forms a right angle at the bottom, and that's going to be our height. Okay? Likewise, for this obtuse triangle here, we have to do a dotted line that forms a right triangle down here, and this is going to be our height. So for triangles, you just have to make sure when you take your height, you're doing the height at the right place. You're always going to drop a dotted line down that's perpendicular to where the base is. Okay? And if you figure out correctly your base and your height, then the area of a triangle will always be 1/2 the base times the height. Or some people like to think of it as base times height over 2. Either way is fine. It'll give you the same answer. But I tend to see it more as, or what I'm more familiar with was 1/2 base times height. But in the book, they had base times height over 2. Now there is another name for the height, and so you may sometimes see this H identified as the altitude. So if they were to give you like a word problem and said the altitude of the triangle was 3 or whatever, that's what they're talking about. They're talking about the height of the triangle. And then the final shape, and I don't know if they actually give you I don't think they actually give you a formula for this. They don't explicitly give you this. So I do want you to see that you can figure this out if you didn't know what the formula was. But let's say we have a parallelogram. So parallelogram looks like this. And for parallelograms, you have similar to a triangle, you've got this base down here that actually, I think I'm going to name it L. But you have to draw, just like we did with the triangle, you have to draw a dotted line down here and specify a height. So actually I think they do. I think base is typically what they use for that. So the area of this parallelogram would be base times height. And you just have to make sure the height, that you realize the height is not this slanted line here. It's a line that you drop down that is at 90 degrees to where the base is. And that's just like you do with the triangle. So that's the area of a parallelogram. I should have written names over each of these. I think you know these first 4, but I just want to make sure everybody knows that that's a parallelogram. And what I want you to see is that if they gave you enough information with a shape like a parallelogram, and this is actually true for any quadrilateral. What's a quadrilateral? You guys know?
4 sides with the same length.
They're not the same length. A quadrilateral is
They're
just
the
any
same
polygon with 4 sides, actually. It can have any 4 sides. It's just like a pentagon is any polygon with 5 sides on it. So a quadrilateral is just any shape that's got, it could be that. Kind of weird, but there it is. It's got 4 sides. The sides are all closed, so it's a polygon with 4 sides. Yes?
Can I use the restroom?
Yeah, go for it. Now, anytime you've got something like this, you can always figure out the area if you have enough information by drawing a line between 2 of the opposite sides. And when you draw that line, now what do I have? I don't simply have a 4-sided figure. I've actually got 2 triangles up against one another. You guys see that?
Yeah.
And we know how to find the area of a triangle. So that's the same thing for the parallelogram. I could take this parallelogram, divide it up into 2 triangles, and assuming they gave me enough information to figure it out, I just take the area of the 2 triangles and add those together. And it'll give me the same thing that the base times the height will give me for the area. So just don't forget that with figures. You can always split the figures up into smaller shapes that you're familiar with and know how to do the area for, and then add those areas together to get the total shape. Okay? So let's do that. Let's do one quick example just to show you a weird one that there is a specific area formula for, but instead of knowing the area formula for this, we can just realize that we know the area for a triangle. So this is what, does anybody know the name of this figure? Trapezoid? Yep, that's right. So Madeline got it right, that's a trapezoid. And when they draw this figure, they say this is 9, this is 15, and then they tell us that this height right here is 4. And let's see if they give us units. It's in meters. And they also tell us that those lengths there are 5 and 5. Okay? So this is actually what we would call an isosceles trapezoid because those distances are the same over there. How would I find the area of this? Well, I haven't given you guys the area formula for a trapezoid, right? But what do we know how to find the area of that will help us find the area of
You
this?
split the two sides into triangles and one rectangle.
Okay, I see what you're saying. So we could do this, right? So that's definitely an idea. So we can go do that. And that would work. Let's see if we have enough information. So we would have to know what this distance is here and here, right, to do our triangle like that, because we got to know the base times the height.
It'd be 15 minus 9.
It would be 15 minus 9 divided by 2. Right?
The triangle, yeah.
Right? So 15 minus 9 is 6, and so that means that each of these sides have to be 3. Because 3 plus 9 gives us the 15 that's down here, right? So that's definitely an option, but there's actually a quicker way. That would work. You just have to realize now that this, that of course this distance down here is 9 also. That will work, or we could do it where we just split it into 2 triangles, right? Because they gave us this height here, we can say this triangle here has a base of 15. This is probably the easiest one to see, right? This triangle here has a base of 15 and a height of 4. So we could say the area of triangle 1 is 1/2 base, which is 15, times a height of 4. Does everybody see that? So that's the area of triangle 1. What about triangle 2? Well, you got to think about triangle 2 sort of being flipped upside down. All right? And so if I think about triangle 2, let's just say I'm going to take this thing, I'm going to flip it over. So that means this guy is going to do like this. And then it's going to go down like this. And this is 9 meters. And we know that this distance here is 4 meters. So I can figure out the area of that triangle as being 1/2, a base of 9, and again, a height of 4. And so for this one, we get 15 times 4, which is 60. 60 divided by 2 is 30. So you get 30 there. 9 times 4 is 36. 36 divided by 2 is 18. And if we add these two then together, area 1 plus area 2, that equals 30 plus 18 equals 48. Am I done? No. What do I need? I need my what? Is it just meters? Meters squared. Square meters, right? So this is going to be meters squared. Technically, I should have put it on each of these as I was calculating. Don't forget your units. That would be our final answer. If we wanted to, as an exercise, we could split it up like Will said, and if we'd done it like he said, we would have gotten the exact same answer. We'd have just had to take 3 calculations instead of just 2, and then add all of those together. All right? Does that make sense to everybody? Okay, so we covered 4 sections this week, so I'll enter your assignment in ThinkWave, but that means we're going to have to do the practice set for all 4 sections, and then the odd-numbered problems for those 4 sections, all right? So this week we're going chapter 5, lesson 5 through 8, and make sure you understand the material well enough to take a quick quiz on it next week. Okay? All right, you guys have a great day.